Have you ever stopped to think about how things, well, connect? I'm talking about everything from your friends on social media to the weather forecast. There's this hidden structure, a set of rules that governs how one thing relates to another. And you know what? It's all built on the simple yet incredibly powerful idea from mathematics. So let's dive in and uncover these hidden rules of connection. Now, I know what you're thinking. My social life is a math problem? It sounds like a stretch, right? But think about it. Every connection you have online, every friend suggestion that pops up, every single ad you see, it's all being mapped out using the mathematical concepts of relations and functions. These aren't just some abstract ideas from a textbook. They are the literal blueprint for how we model and make sense of the connected world all around us. You know, the best way to wrap your head around this is to picture a function as a machine. It's simple, really. You put something in, that's your input, and the machine follows a very specific rule to give you something back. That's your output. This whole machine idea is the key that's going to unlock everything we talk about today. Why? Because it's predictable, it's reliable, and it is incredibly powerful. Okay, but to truly appreciate just how precise this machine is, we first have to go back to the beginning. We need to explore let's call it the chaotic universe of raw material that it's built from. We're talking about the simple, unrestricted idea of connection itself. And that brings us to our real starting point, the concept of a relation. Think of this as the wild, untamed frontier of connections, where basically anything and everything is possible. So what is a relation, officially? Well, it's just any collection of connections between two groups of things. Let's say we have a starting set, we'll call it set A, and a target set, set B. A relation simply picks and chooses pairs, linking an item from A to an item from B. And that's it. Seriously, no other rules apply. Anything goes. To see just how much potential for chaos we're dealing with, we need a map. A map of every single possible connection that could ever exist between our two sets. In math, this map is called the Cartesian product. So if set A has the numbers 1, 2, and 3, and set B has 1 and 2, this table right here lists every single possible pairing. A relation can be any group of these pairs you can think of, maybe just one of them, maybe all of them. This is the entire universe of links we have to play with. And this really gets to the heart of what a relation is. It's pure potential. It's chaos. An item in set A can connect to absolutely nothing in set B, or it can connect to everything in set B. There are zero restrictions. It's flexible, for sure, but that also makes it completely and utterly unpredictable. So, the big question is, how do we get from that chaos to the orderly, predictable machine we were talking about earlier? Simple. We introduce rules. And it's these rules that separate a mere relation from the absolute superstar of mathematics, the function. Let's put them side by side so it really clicks. A relation? That's the Wild West. Unruly, unpredictable, anything can happen. A function, on the other hand, is that reliable machine. And it gets its reliability from two very strict rules that turn a simple connection into a predictable process. Here's the thing to remember. Every function is technically a relation, but it's a very special, very well-behaved one. So what are these magic rules? Well, first, you've got the no ghosting rule. In a function, every single item in your starting set, your set of inputs, has to be connected to something. No input gets left behind. And second, we have the one and only rule. This means every input can only connect to exactly one output. Not 0, not 2, just 1. So what happens when these rules get broken? Well, let's take rule number 1. Imagine an input that has no connection at all to any output. It's been ghosted. This immediately disqualifies the whole system from being a function. A reliable machine would be broken, right? It would get an input and have no idea what to do with it. Okay, now let's break the one and only rule. Picture a single input that connects to multiple different outputs. This creates a massive problem for predictability. If you put one thing into our machine, you need to get exactly one thing out every single time. If you get 2 or more possible answers, you've introduced uncertainty, and that means it fails the test. It is not a function. All right, now that we've nailed down the rules, we can finally look inside our machine and label its key parts. There are 3 core terms that you really need to know to describe a function's anatomy. First up, the domain. That's just the official name for our starting set, the set of all possible inputs. Simple enough. Second, we have the codomain.
This is the entire universe of possible outputs. Think of it like all the possible destinations an airline flies to. But the specific cities today's flights are actually going to, that's the image. The image is the set of actual, real outputs the function produces. It's a specific selection from all the possibilities over there in the codomain.
But here's where it gets even more interesting. Even within these strict rules, functions can have different personalities, and these personalities determine the precise nature of the connection they create, giving us a few distinct types to explore. These personalities give us three main types of functions. First, there's injective, or one-to-one. You can think of this as the no-sharing rule. Every input maps to its own unique output. No two inputs can ever point to the same result. Next up is surjective, or onto. This type of function is an achiever. Its whole goal is to cover every single possible output. Nothing in the target set is left unused. And finally, we have the bijective function. This is the gold standard, a perfect match. It's both injective and surjective, which means every input has exactly one unique output, and every single possible output is accounted for. It creates a perfect, reversible pairing between the two sets.
So we've gone from relations to functions, and now we even have different types of functions. But why does any of this matter outside of a math classroom? Because these rules, this structure, this is what allows us to build predictable, reliable systems in the real world.
I mean, these concepts are the invisible architecture of our modern world. When meteorologists model weather patterns, they're using functions. An input of current atmospheric data produces a predictable output, tomorrow's forecast. When social networks suggest friends, they're using functions to map your connections to a set of probable new ones. Even complex, beautiful art like fractals are just a simple function applied over and over again. By turning chaos into predictable order, functions give us the power to model our world, and in a lot of cases, to predict its future.
So the next time you check the weather or scroll through your social feed, just remember the hidden machinery working behind the scenes. From that wild west of chaotic relations, we create these ordered functions that basically run our world. Which kind of makes you wonder, right? What other parts of our daily lives are secretly being guided by these same simple, powerful rules?